Here's something that should bother you. Every major AI lab is racing to ship data science agents. Drop in your dataset, get a trained model. Sounds great. But when researchers actually tested whether these agents follow instructions, not just produce outputs, they found something disturbing. Models that scored well on final accuracy were ignoring explicit constraints, skipping pre-processing steps, using algorithms you told them not to use, and still stumbling into correct answers. That's not intelligence. That's a coin flip that happened to land right. This paper is called Dare Bench, and it's the first benchmark that separates getting lucky from actually knowing what you are doing. Let's break it down. Most benchmarks for LLM data science agents measure one thing: final prediction accuracy. Here's the problem with that. Imagine you are hiring a manager. A candidate submits a data analysis project, the final numbers are correct. But when you look at their code, they used test data during the training. Classic data leakage. They ignored your requirements to use logistic regression and used XGBoost instead. They didn't handle missing values. The model just happened to work anyway. Would you hire them? Of course not. The person got lucky. But that's exactly how we have been evaluating LLMs. Final output only. No process audit. Their bench introduces a concept called instruction fidelity. Did the model actually do what you asked, the way you asked, at each step? And here's the uncomfortable finding. These two metrics diverge. Models can score high on accuracy while scoring terribly on fidelity, which means we have been training and rewarding models for the wrong behavior. What their bench actually measures? So let me explain the architecture because the design decisions matter. So their bench team had 6,300 tasks derived from real Kaggle competitions, not synthetic toy problems, and actually messy datasets with real ML challenges. Each task has a natural language instruction, what the user wants, structured data files, train split, test split, metadata verifiable ground truth, objective, reproducible scoring. The model operates in a sandboxed environment with code execution. It writes code, runs it, produces predictions. Those predictions are compared against ground truth automatically. No LLM as judge, no human evaluator, fully deterministic. That matters because most modern evals have another model deciding what's good, which introduces bias and inconsistency. Now, here's the key innovation. Darebench tracks two separate scores. First, outcome accuracy. Did your predictions match ground truth? Second, instruction fidelity. Did you follow the constraints? If the instruction said use random forest, did you? If it said don't use feature X, did you respect that? These scores can completely diverge. Model can ace accuracy and fail fidelity. That divergence is the whole point. It reveals whether the model understood the task or just got lucky. Let's talk findings. This is where it gets uncomfortable. GPT-04 Mini, OpenAI's small reasoning model, struggles significantly on their bench modeling tasks. This is a model that crushes math Olympiad problems, coding challenges, logic puzzles, but multi-step ML workflows with domain constraints, it fails apart. Why? Because data science is not a clean puzzle. It's a messy process requiring domain knowledge. When to normalize, why you would pick gradient boosting over linear regression for the specific distribution, how to spot feature leakage. You can't pattern match your way through that. You need to actually understand. But here is where it gets interesting: the training result. The researchers used their bench training tasks to fine tune models. Supervised fine tuning on Quen 3 32 billion parameters, 1.83 times accuracy improvement. Reinforcement learning on Quen 3 4 billion model, it took over 8 times improvement. 8 times on a 4 billion parameter model. That's not incremental, that's a category shift. What this proves is that the bottleneck is not the model architecture or the parameter count, it's training signal quality. When you give the model feedback that rewards process fidelity, not just final output, performance explodes. This validates what the reinforcement learning for reasoning community has been arguing: verifiable. Objective reward signals are disproportionately powerful. Darebench provides exactly that. Let me zoom out because there is a strategic point here. The AI plus data science space is splitting into two camps. Camp 1: just use GPT-4, it's good enough. Camp 2: fine tune smaller specialized models on domain specific data. Darebench is strong evidence for Camp 2, but with a crucial caveat. It's not just about fine tuning, it's about what you fine tune on. The real bottleneck is not compute or model size, it's the scarcity of high quality, process aware, executable data science traces. Training data that captures not just the correct answer, but how a competent data scientist would have reasoned through it. This is the same evaluation code generation went through. Models get dramatically better when we stopped rewarding outputs that look like code and started rewarding code that actually runs and passes tests. Darebench brings that same rigor to data science workflows. And the instruction fidelity metric has immediate implications for anyone building agentic systems. If you are building a data pipeline agent and you give it constraints, use only these features, don't touch that column, Darebench shows that even frontier models don't reliably follow those instructions across multi-step workflows. That's not a prompting problem, that's a training problem. And now we have a benchmark that measures it. What to watch? A few open questions this paper raises. Generalization beyond Kaggle. Kaggle has clean train test splits and leaderboard metrics. Real world data science is messier. Extending this to enterprise pipelines, time series forecasting, or domain specific science is the next frontier. RLVR as the key lever. The 8 times improvement via reinforcement learning is not accidental. It's the same mechanism behind reasoning models. Now, applied to structured domain workflows, expect more papers here. Process fidelity as a standard metric. I would like to see this on model cards. Our model achieved a X% accuracy and Y% instruction fidelity on their bins. That tells you far more than accuracy alone. Right now, we are celebrating AI's ability to do data science by watching it get right answers. But a doctor who reaches the correct diagnosis by skipping steps and ignoring symptoms is not a good doctor. They are a lucky one. Darebench is the protocol audit, and most models are failing it. Here is my question, and I actually want to know: are you using LLMs in your data science workflows? Do you trust them to follow multi-step instructions, or do you manually verify every step? If you have been burnt by a model that got the right answer but completely butchered the process, drop that story in the comments. I bet there are some disasters in there. Like if you think process fidelity should be standard on every model card. Subscribe if you want more breakdowns like this. See you in the next one. Thanks. Bye.